Okay, so
Are you telling her to not apply for college right now?
yeah. We are going to be talking about the easy shortcut formulas to find the derivative. We are going to be using the derivative and the derivative formulas the rest of the year. It doesn't go anywhere, but now I would like to be able to show you the shortcuts. So remember that the derivative is a instantaneous rate of change, and it is the slope of the tangent. If you are trying to find the derivative of a constant, it is always going to be 0. Now think about the slope of a horizontal line. It is 0. So your first formula to remember is if you are taking the derivative of 2, the answer is 0. Of 7, the answer is 0. 46, the answer is 0. If you are taking the derivative of a constant, you are always going to get an answer of 0. If you apply the formula, you always get c minus c over h, which is going to then give you 0. Okay, so that's your formula. The derivative of a constant is 0. This just says, hey, if you take the derivative in terms of x of a constant, any number, so if your function is 7, the derivative of that is 0. So that's just your first rule. You need to memorize that the derivative of a constant is 0. Next formula, let's talk about power functions. So power function is of the form f of x equals x to the n. If you have f of x equals 1, no, if you have f of x equals x, the derivative is 1. So f of x equals x, the derivative is 1. Now it correlates a linear expression. The derivative of it will always be the slope of that line. So if you have a function in the form y equals mx plus b, the derivative is always going to be m. It's always going to be that slope. And it's just because it's kind of tangent to itself along every point. I mean, it's just, there's no other way to distinguish from the tangent and the slope. They're always going to be the same. But let's take a look at some things here, and let me see if you can see the pattern that's happening. If you're taking the derivative of x squared, you get 2x. If you take the derivative of x to the third, you get 3x squared. Take the derivative of x to the fourth, you get 4x cubed. Anybody see the pattern besides Ryan? Oh my goodness, you have found the pattern. So for a power function, the rule is exactly what you guys noted. The power drops down in front. The power goes down by 1. For a power function, the rule is the power drops down in front. The power goes down by 1. So, if we took the derivative of that x to the fifth, like was noted, the derivative is just 5x to the fourth. If we took the derivative of x to the seventh, it's 7x to the sixth. If we took the derivative of x to 100, it's 100x to the 99th. So that rule is just an essential rule for finding the derivative of a power function. So that was 99. Yeah, you can't read my wrist right. So let's talk about some functions where this rule can benefit us. If we are trying to take the derivative of a square root, let's say we're trying to take a derivative of a square root, rewrite that as a power function. So if we're trying to take the derivative of x to the 1/2, drop the power down in front, the power goes down by 1. Now, we have been taking derivatives of square roots, and we keep kind of getting a 2 appears, and our square root goes in the denominator. That's what that negative power does. So it kind of makes sense, right? For a If we're trying to take the derivative of 1 over x, how could we rewrite 1 over x as a power function? X to the negative 1. And as soon as it becomes an x to the negative 1, we can use our rules of power functions. Drop the power down in front, power goes down by 1. You might have noticed that we were getting a lot of 1 over x squareds or negative 1 over x squareds when we were doing those fractional ones. And that's why. So the rule is, if we are taking the derivative of a power function, drop the power down in front and take the power down by 1. Now, the next rule allows us to have a constant stuck to anything. And that constant, you'll notice, just goes out in front and just hangs along for the ride. Let me give you an example. Let's say that we are taking the derivative of 6x to the second power. If we want to derive that, the power drops down in front and just multiplies by the 6 that's already there. So the 6 just hangs along for the ride. And so the answer is 12x. Okay, so the derivative of a power function that has a constant in front follows the power function rules, and you just multiply by that front constant. So that allows us to just use a lot of those particular types of rules. This next one allows us to add two power functions together. Why aren't you taking notes? That's okay. Okay, so let's say that we are trying to derive 5x squared plus 3x plus 7. We now know the rules to do it very, very quickly. So a polynomial like that, each individual term is a power function that may or may not have a constant on it. And so if we follow the rules, this first one, the 5 sticks along for the ride, we multiply by 2, the power goes down to 1. The 1 drops down, the power goes to 0. What is the derivative of the constant 7? What is the derivative of a constant? 0. So our answer is 10x plus 3. A lot quicker than what we were doing. Now think about if we had to apply the formula to 5x squared plus 3x plus 7. We would have to stick the x plus h in. We would have to square it, multiply it by 3, add 7. It would be a very long process. But look, we took the derivative in 5 seconds, okay? Because of the fact, see how we, this one? 0 power. Because it was a power of 1, so that's why it becomes a power of 0. And see how that one, that's where the 3 is. A derivative of a linear function we talked about is just the slope of that linear function. So if we had the function y equals 3x, the slope is 3, the derivative is 3. Of course not. I'm just showing you how the rule works. So yeah, once you get to the fact that you know that 3x's derivative is just 3 and the 7's derivative is just 0, just writing 3 is perfect. Yeah. So if you don't if you don't see the power, remember it's a 1. If you don't see an x, to remember the rule, you could have tacked on an x to the 0 there if you wanted. It does work. So you could, for the 7, you could write that as 7x to the 0, and it does, the power rule then will work for you if you forget it. Okay. You can add or subtract, so it doesn't matter whether you're adding things or subtracting things. The negative 1 just acts like a constant. It just hangs and comes along for the ride. Okay. Be careful of this piece if you are subtracting, if you have multiple pieces, just like in the derivative formula, use parentheses if you need to. Okay. So that gives us, we can now take the derivative of any polynomial or any combination of power functions very, very quickly. So that just will make your life much easier than when we originally were doing this, okay? Hi. So let's take these derivatives really, really fast, okay? Okay, so our first one here is a power function. So to take its derivative, drop the power down in front, power goes down by 1. Bam, we're done. Let's do C that's underneath it just because it is. Now, you'll notice we're taking the derivative in terms of t. So our function is a t. So it just follows a power rule. So the 4 drops down in front, power goes down by 1. Bam, we found the derivative. Okay. B, doesn't matter even if it's a power of 1,000. 1,000 drops down in front, power goes down by 1. That y prime notation just means we're taking the derivative of y with respect to x. And that's an x there, I'm sorry. That's an x there. And here we're taking the derivative in terms of r's, so treat the r like our variable. So the 3 drops down in front, power goes down by 1. So derivatives of polynomials or combination of polynomials are quick and easy. But you got to remember your rules. Power drops down by in front, power goes down by 1. Okay, and if you have a list of them, you're going to do it very quickly. Now, these are the ones where looking at it initially, they look yucky, but they are not if we rewrite as a power function. So how could we rewrite this one as a power function? Yes, x to the negative 2. Now that is not the derivative. I'm just rewriting it so I can do the derivative. So the derivative is negative 2x to the negative 3. Now remember what happens. The power drops down in front. The power goes down by 1. Negative 2 minus 1 is negative 3. So it becomes more negative, if that helps. If it's a negative, when you subtract 1, you're really adding another negative, and that's why it becomes a negative 3. So it becomes more negative. Okay. Square roots, any type of radical function can be rewritten as a power function. Let me remind you of the rule from algebra class. If we have, that's an m. If we have an index of m and a power of n, remember the top of your fraction is your power. The bottom of your fraction is your index. So that's your power and that's your index. Now that's just a rule from algebra that you should know. If you don't know that rule, rethink your algebra skills, but you need to know that rule, okay? So if you look at that, so this is going to be our denominator. And this is going to be our numerator. How do you spell numerator? There we go. Thank you. I can't spell. Anyway, so you first are going to write this as a 2/3 power. Now we are ready to use our power rule. If you can rewrite something as a power function, do it, because power functions are easy to take a derivative of. Okay, now that we know the rule. So for the derivative of this, the power drops down in front. Now let's think about when we subtract 1 from 2/3. 1 is 3/3, so 2/3 minus 3/3 is negative 1/3. Okay, so the rule is rewrite as a power function when possible, Use your power function rule. Power drops down in front, power goes down by 1. Power drops down in front, power goes down by 1. Everybody okay with that? Okay. So now let's practice doing find the equation of the tangent line in a quicker way. So in the past, when we've found equations of tangent lines, we started out kind of guesstimating where they were. Then we went to that long formula to find the slope of the tangent. Well, now we have some shortcuts. So if you want to find the equation of the tangent line, it should occur to you immediately, I need to do the derivative. That's my first step. So remember, first step is find the derivative. Wow, that looks horrible. I'm so sorry. Second step, find the slope of their tangent. You might have to plug, it in somewhere. The third step is use y minus y1 equals m times x minus x1. So that is always the procedure that you want to follow. That's a procedure we've been following straight from the beginning. Now, step 1 is a lot easier. That's the only difference, okay? So the first step we're going to do is to find the derivative. So let's analyze this for a minute. Remember, rules of derivatives say that so far we know how to do power functions very easily. So if we think about that as x to the first times x to the 1/2, we don't know how to do a product of things, but we do know how to do a power function. What are the rules of algebra that say I can combine those things? If the bases are alike and I'm multiplying, I can do what to the powers? Add them. So 1 is 2/2 plus 1/2 is 3/2. Now that looks very nice because now I'm ready to use my power rules, right? So the derivative, I drop the power down in front, the power goes down by 1. 3/2 minus 1 is 3/2 minus 2/2, or 1/2. Okay, so that's step 1. I found my derivative. Step 2 says to find the slope of the tangent. Now, we're finding the slope of the tangent, excuse me, when x is equal to 1. So we get to just plug in 1. 1 to any power is still 1, so the slope of our tangent is 3/2. So now we're ready to use the point-slope formula. We know the point, we know the slope. Now we're back to algebra class. Y minus y1 equals m times the quantity of x minus x1. That shouldn't be any like magical thing. So it's just y minus y1 equals m times x minus x1. Now, I'm okay if you stopping there. I know you know how to rearrange that equation. It's not a bad idea to get it in slope-intercept form. If we do, we would get the following equation. And I have a graph there, and I'm sorry my graph is so little. I was trying to hide it from you, but I forgot then. The app that I was using initially, I could blow up a picture, but I can't. But you can see here, that's the y equals x to the 3/2 function. At 1, 1, we start at -1/2, we go up 1 over, or up 3 over 2. But anyway, that is our equation. You can kind of see it there a little bit. Okay, so this should not be some magical thing. You should hopefully understand this process because now we know the derivative formula for it, bam, real quick. So you have to memorize that formula. That formula is not going anywhere. We're using it the rest of the year. Okay, everybody okay with that example? I told you this lesson's nicer than the others. So we can do derivatives now pretty quick. It's just recognizing the rule, okay? So our first one here, the derivative is just going to be 3 comes along for the ride. The 4 drops down in front, multiplies by whatever coefficient is already there. Power goes down by 1. And then just rewrite that. Now, you can do 3 times 4 in your head. So if you just immediately wrote down 12x to the third, great. This is a power function. It doesn't look like a power function, but it's a linear power function. So it's just the slope of that line, which hopefully you just recognize as -1. But let me show you why the rule works the way it does. There is a -1 constant. The 1 drops down. Power goes down by 1. But the answer is the coefficient. So the rule is, if you are taking a derivative and there's a coefficient on a plain old x, the answer is always that coefficient. Okay, if you are taking the derivative of a 2x, the answer is 2. 7x, the answer is 7. 5x, the answer is 5. So it's always going to give you the constant that's stuck on our x. So if we apply everything we know, those singular power functions lead us to just a big long polynomial. Think about doing this the formula we had to that. That would take you all day and 4 sheets of paper, okay? But now, look at what we can do. We can do each individual term, because we know that the derivative of a sum, you just do each individual piece that was added together. So this first piece would be 8x to the 7th. The second piece, the 5 would drop down and multiply by the 12, giving me 60x to the 4th. 5 times 12. The next piece, the 4 would drop down in front, multiply by 4. That's -16x cubed. The next piece, the 10 would multiply by the 3. I have to drop down, and the power would drop down to 2. Here is the constant I was talking about on an x. It's just going to be that constant. And the derivative of that is just 0. Now, if you put a +0, I'm okay with that. It doesn't hurt anything. But the derivative of a plain old constant is always 0. You don't have to. If you want to, feel free. Does everybody see how that's our derivative? Okay, so polynomials are awesome. They're good in so many ways. The graphs of them, the derivatives of them, the intercepts, all those things, because polynomials are so nice, they follow lots of good rules. Let's take a look at example 6. So it says, find the point on the curve where the tangent lies as horizontal. Now, let's analyze what that means. A horizontal line has a slope of what? 0. So this is really just saying, where is the slope of the tangent equal to 0? That's all that says. That is just a fancy way of saying, where is the slope of the tangent equal to 0? Well, what is the slope of the tangent formula? The derivative. So that is really saying, where is the derivative equal to 0? Now, we know how to do stuff like that. To find where a function is equal to 0, sometimes you factor it, sometimes you know, but let's take a look. Y prime in this particular case is a string of individual power functions that we've added or subtracted. So we can just do it real quick. 4 drops down in front, power goes down by 1. There's already a -6 there. When I multiply it by 2, I get a -12. Power goes down by 1. The derivative of a constant is 0, so the 4 isn't a factor. So we're really looking, where does 4x cubed minus 12x equal 0? So that goes back to algebra class. Where does 4x cubed minus 12x equal 0? Usually for a polynomial like that, the most effective way to find where it's equal to 0 is to factor it. If it's a quadratic, like a second power, we can use the quadratic formula if it's not factorable. So there are times where we will get funky answers to these, like the square root of 12 over 6, or something like that. Okay. But this one, they both are divisible by 4, both terms, and both terms contain an x. So let's take out a 4x. And when we do that, we get x squared minus 3. Now, you can kind of break up x squared minus 3, which I'll talk about in a minute, but you can now just kind of separate them. And solve each one individually. So this is 0. This is plus or minus the square root of 3. So where's the slope of the tangent line horizontal? At 0 and at plus or minus square root of 3. Now, x squared minus 3, you can actually split up using the difference of squares formula. That would be x plus square root of 3 and x minus square root of 3. So feel free to even split it up further at this point. Your Algebra 2 teacher or Algebra 1 teacher might have misled you, saying that I can only factor that if it's a perfect square. Well, is square root of 3 a number? Yeah. So can I break it up? Yeah, I can. Okay. This method might prevent you from forgetting the plus or minus. I know many of my students will forget that there's a plus or minus symbol there. So if this helps you avoid that mistake, break it up. Okay. Now, if we look at the graph, my teeny tiny little graph here, look and see where the zeros are. Where are they 0? At the bumps, the hills and valleys. So the tangent being horizontal actually locates those hills and valleys for us. So that's what negative 1.732 is the square root of 3. And you'll see that we do have horizontal tangent lines at those 3 locations. I know, my little bitty graph. Okay, so you have to recognize really what they're asking you. So you need to now put into your memory banks that if they say, where is the tangent line horizontal, they are really asking, where is the derivative 0? You have to put those things together, and that will prevent you from making mistakes in the past. Okay, so that leads us, wait, let's see, how many slides do we got? Oh, we're almost done. So you'll notice that we were given the sum and the difference of individual pieces that we were allowed to differentiate each individually and then add them up or subtract them. But if 2 things are multiplied together, it is a much more complicated process to find the derivative. So I am going to say this so many times, you're going to get sick of it, but it will sink into your brain a little bit. That if we have f times g, the derivative is the first times the derivative of the second plus the second times the derivative of the first. The first times the derivative of the second plus the second times the derivative of the first. You have to have that rule memorized. There is a product rule, there is a quotient rule. We have to have that rule memorized. We are going to make some flashcards with some of our most important rules on them. We'll probably do that tomorrow. So just so you know, you have to have this memorized. So I am going to say 1,000,000 times, the first times the derivative of the second plus the second times the derivative first is how we take the derivative of a product. So if we have something times something and they've asked you to find the derivative, we have to do each thing individually in that step. So let's go over what that means. The first times the derivative of the second plus the second times the derivative of the first. What does that mean? Now, I'm going to show you an example that technically we don't have to use the product rule, but it will illustrate the point. So if I say to find the derivative of 6x cubed times 7x to the 4th. Now, in real life, I would never use the product rule, because couldn't you take and make that 42? Couldn't you make that 42x to the 7th? So the derivative is just going to be 42 times 7x to the 6th. So you don't have to do the product rule on this one, but the product will allow me to show you that the answer is really 42 times 7x to the 6th, okay? So it's just an illustration of how the formula works. So I'm going to call this my F, and I'm going to call this my G. So it's a product of two things. And if they ask you to find the derivative, we have to apply this formula, okay? So the derivative is going to be the first function, just write it down, times the derivative of the second function. Now, the derivative of the second function is, how do I take the derivative of a power function? I'm going to do 7 times 4, and the power is going to go down by 1. Now, the rule is first times the derivative of the second plus the second function, just write it down, times the derivative of the first function. Well, the first function is a power function, 6x cubed. How do I take that derivative? Well, that's just going to be 6 times 3, or 18. And 18 is going to be followed by an x to the second power, because the power goes down by 1. Now, up above, I said I'm claiming that my answer is going to be 42 times 7, x to the 6th. That's 294 x to the 6th. Now, let me show you that's what we get. 6 times 28 is 168. So that's 168 x to the 6th. 7 times 18 is 126 x to the 6th. So we have a total of 294 x to the 6th. So it is correct. It does work. I would never use it for this problem. Okay? You don't have to use the product rule if I can take the product first. Okay? So if I can change it into 42x to the 7th, I would do that, and I would get a derivative of 294x to the 6th. But this shows you how the power function works. So it is, you write down the first, take the derivative of the second, plus the second, write it down, times the derivative of the first, okay? So you have to remember this rule. I can't tell you how important it is that you know that rule, okay? So that's the product rule. There's also a quotient rule. The quotient rule is just as important if we have two things that are divided by each other. So let's write this. I'm sorry, I just couldn't at the time when I made up this slide. Let's write that as F divided by G. If we were taking the derivative, I always say it in my brain as the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom square. Now, I will tell you, consistently my students mess up this formula because they don't start with the bottom. They don't remember to subtract. The product formula is addition. The quotient formula is a subtraction. So let me say it again. It is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. You have to memorize that formula, okay? Super, super important, because there are some things we can't divide nicely. So this formula allows us to take a derivative of a fractional function very quickly. We can even apply this formula to 1 over x. You do the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. We get negative 1 over x squared. Bam, it is what we got using it as a power function. So if it's fractional, you can use this no matter what. Okay, let's look at an example. We have a polynomial. It's not really divisible, so we're kind of forced for this one to show you what the derivative is. Okay, so let's put both top and bottom in parentheses. So it's a quotient. The quotient rule says that the derivative of a fraction is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Okay, so let's do the derivative. So we're going to write down the bottom. We're going to do the derivative of the top. We know how to do the derivative of that. We just do each individual term using the power rules. So it's going to be 2x plus 1 minus the top in parentheses times the derivative of the bottom, 3x squared, all over the bottom squared. Now, I'm not wasting time now. We don't have the time right at the moment. But in real life, you would never multiply the bottom out. It's not helpful, but you would simplify the top. Just using your rules of algebra, distributing, combining like terms. Okay? So let me say it again. It is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. Leave them in parentheses until it's time to distribute. The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. That is the rule. That is the formula. You need to memorize it. Okay. So last example says to find the equation of the tangent line and the normal line to the curve at the point 1, 1/2. So the first thing we have to do is to find the slope of our tangent. We'll talk about a normal. It's just perpendicular to the tangent. We'll talk about that in a minute. But so the slope of our tangent is just the bottom. This is the derivative formula. Let's call it the derivative. So the derivative is the bottom times the derivative of the top. We're going to call that x to the 1/2 so we can use a power rule. Minus the top times the derivative of the bottom, all over the bottom squared. Now, do not do a darn thing to that. We know how to plug in numbers nicely, right? What is our x value we're plugging in? 1. Let's plug it in. Let's not worry about doing a darn thing to make it pretty because we don't care. We just need the number. So if we plug in 1, we get 2 times 1/2 minus 1 times 2 all over 1 plus 1 or 2 squared. 2 times 1/2 is 1. 1 minus 2 is negative 2 over 4. The slope of the tangent is negative 1/4. That wasn't horrible to plug in. So now the equation of our tangent line is just y minus 1/2 equals negative 1/4 times x minus 1. There you go. Got the slope of the tangent. We got the equation of the tangent line. They did also mention the normal line. If the slope of the tangent is negative 1/4, the slope of the normal is just the flip of that, the reciprocal of that. They're perpendicular lines. So it's just negative. Just flip the sign and then flip it. So it's positive 4. So the equation of my normal line is just y minus 1/2 equals 4 times x minus 1. So if they ask you to find a normal line, just do the tangent, find its slope and flip it over, and you've got the normal line. It's nothing, it's not mathematically more that you have to do. This kind of is going to guide you. The normal is just the opposite reciprocal slope. Okay. So that is that, and that kind of leads to all of these derivatives. Now, I know the bell's going to ring, but just follow along with me for a minute. 1 through 4 is ready to go. 5, 6, 7, 8. Some of those, it is much more easier to do it if you have to make that prettier first. We're going to do some of these tomorrow. Together, that's what we're doing in class. We're just working on these, working on these, working on these. That's it. Yeah. Okay. No problem. I'm so glad you paid attention. It's great.